This video will be about calculating the magnetic force on a charged particle moving through a magnetic field. A version of these notes can be found on May 7th. There's a textbook reading that you should probably watch or read through, and a little video that is somewhat interesting. It helps enrich this content. But from the last video, the magnetic force was shown that it equals to the velocity of the charged particle multiplied by the magnetic field, and that the velocity and the magnetic field were perpendicular to the force. So if velocity is in the x direction, magnetic field's in the y direction, that means it will be perpendicular to the z direction, which is where the force would be in. If v was in the z and b was in the y, then your force would be in the x direction. If the velocity vector and the magnetic field vector are not perpendicular to each other, then you multiply by sine of the angle difference between them, and that will give you your force. Units for the magnetic field, remember, is a Tesla, and a Tesla is the equivalent of a Newton per coulomb meter per second. In another video, I'll explain current, and when that happens, you can change this unit as a Newton per amp meter, but that's still another video away. So we'll get into it. Suppose you have a proton. It enters into a uniform magnetic field of magnitude 0.25 teslas. Just as a heads up, all of your magnetic fields are going to be uniform. You're not going to have a changing magnetic field for the most part for most of these questions, because a lot of the times that will probably involve you dealing with calculus. And you're not there yet. So we can see that the magnetic field is going into the page because of all the x's, so it's in the z direction. And the proton is moving to the right with a velocity of 4 million meters per second. And the question just wants to know what is the magnitude and direction of the instantaneous force exerted on it. So I will do the direction first, because that's typically what I think is the easiest thing to do when you know the direction of the magnetic field and the velocity. So you would get your right hand rule out, you'd put your middle finger, the business finger, down, touching the page, or in this case on the screen. The velocity vector, your pointer finger, points in the direction that the particle is going to go, so that's going to the right. And so when you make the gun with your hand, your force is going to point upwards. So your force should be in the y direction. So I'm going to call that the positive y direction as far as vectors are concerned. It wasn't defined on the page where positive was, up, down, left, right, or whatever. But I'm just going to go with the normal nomenclature of positive is going up on the page. I'm not going to use the word up, though, because sometimes out of context, up can be interpreted as up off the page. So I'm just going to stick with the unit vector, the j with the hat. So the unit vector j with the hat just means it's in the y direction, which is implied going towards the top of the page. So that is going to be my direction. Got that down. Next, I'll just calculate the force. This sine theta, since my velocity vector and my magnetic field are perpendicular to each other, so my velocity is in the x direction, my magnetic field's in the negative z direction, that means they are perpendicular, so sine of 90 degrees is 1. So I'm just going to ignore that sine theta from this point on and just multiply all those variables. So I have a proton. You'll notice there's no number in the question as far as the charge is concerned. So the proton is your base fundamental charge. So that is just 1.602 times 10 to the negative 19 coulombs, multiplied by my 4 million meters per second, and then multiplied by my magnetic field. And I rarely actually put down the symbol Tesla unless I'm solving for a magnetic field. I'll usually write it down as a Newton per coulomb meter per second, because I typically like to see that my units cancel out. An old habit. So when I multiply all those together, the denominator here for the Tesla cancels out the coulomb and the meter per second, and you should be left with a Newton. Probably only should have 2 significant figures, but I wasn't thinking when I take this out. So 1.602 times 10 to the negative 13 newtons is the strength of the force, which sounds like a very small number. It is a small number, but I'll put it into perspective in a second. So if you actually make it a vector notation, which you probably should, because the question says what the magnitude and direction, so vector notation, there's the arrow, and I'm just going to put the unit vector j right after it, and that should be enough. If you wanted to kind of have an idea of what that strength is, you would basically solve for the acceleration on that particle. So the mass of a proton is about 1.67 times 10 to the negative 27 kilograms. So if you divided your force by the actual mass of a proton, you'd get an acceleration that is somewhere around 10 to the positive 13 meters per second square, which tells you that it has a great acceleration, which technically tells you it should break the speed of light within half a second, which we know is not true because nothing can go faster than the speed of light. But that just tells you essentially how strong that force is on a particle. This is a very weak force if it's on a human, but if it's on an actual individual particle, which have a very, very, very small mass, it's going to cause that particle, that proton, to accelerate and move ridiculously quick in a new direction. So the next part of the question, I'll just zip to it. How would it change if an electron were moving through the field? So if electrons moving through the field, I don't know if you noticed the hand on the right. I'll go back a slide. All right, the hand on the right just suddenly switched. It's no longer the right hand, it's now the left hand. Whenever you're dealing with an electron, we don't use the right hand rule. Well, you can use the right hand rule, you just have to remember to make the force in the exact opposite direction. So I typically, when I hear the word electron, I'll just grab my left hand because that's easy enough to do. It doesn't really matter otherwise. So if it was just an electron going through there, you would just make it travel in the exact opposite direction. So if the proton's going in the positive J direction, so positive Y, the electron's going in the negative J unit vector direction, so negative Y. And the numerical value would not change because the charge of a proton is the same as the charge of an electron, albeit opposite in charge, but numerically in magnitude, it is the same charge. So it would just go in the opposite direction. If you were to figure out the acceleration of the electron, it would have a much greater acceleration because electrons are almost 1/2000th the mass of a proton. So that's something for another day. So suppose we have a proton traveling at a velocity, entering a magnetic field B, kind of like the question we just did there. What actually happens? So you've got a force that's acting perpendicular to your velocity. So we know it's going to curve, right? Whenever you have a force acting perpendicular to a velocity, you have uniform circular motion. And in this case, if you actually take your right-hand rule, so we know we're going to assume it's a positive charge, we weren't told otherwise. If you curve that thing through, you can see that no matter what, your force is still going to be pointing towards some imaginary center. So if a charged particle goes through a magnetic field, in this case, magnetic field in the negative Z direction into the page, it's going to cause this positive charge to rotate counterclockwise, while the force is always pointing in a direction towards some imaginary center of some circle. So it's definitely undergoing uniform circular motion. And in this case, this little positive charge is going to enter in and then leave the magnetic field. So it does a complete 180. If the magnetic field was large enough, you would see that positive charge just constantly going around counterclockwise and this magnetic field going into the page. If it was a negative charge, it would travel in a clockwise direction because you'd use your left hand, as the velocity initially was going up in the Y direction. So that just tells us we have to combine a past unit into this. So we know that the force experiencing, the force on this moving particle is the magnetic force. But if it's also undergoing circular motion, then there is an equivalent centripetal force acting on this particle. So we can make those two equal to each other and figure out what either the radius is, or figure out if we can measure the radius with some detector, we can figure out what the mass of these particles are. So what you'd basically do is you'd make them equal to each other, right? So anytime you have a particle or a mass that is moving in circular motion, then your centripetal force is the net force. And therefore, if you know that the cause of that circular motion is your magnetic field, therefore you have a magnetic force, you would just make those two equal to each other, right? And then from this point on, and this is, I don't usually remember these bottom two equations, I always just do this in my own personal work. From that point on, you would just kind of read the question. Some questions will say, hey, what is the radius of curvature? And then you'd manipulate this equation, solve for the radius of curvature. It might look like that. What is the mass of the particle? So very often, you would find something like the mass, or if you know what the actual charge is, you can figure out the mass of the particle that is in that magnetic field. And so those are practical things that scientists actually do use with your magnetic field, observing that particles can go in circular motion. So those are just two little small equations. I generally don't ever remember those. I always just start with this because I know Newton's second law very well, and I can make any equation equal to anything I want, usually. Sometimes I still screw up. So let's go back to this original question. We have a proton entering into this magnetic field consisting of field lines pointing into the page. So it's the same question set up as the first one. We know it's going 4 million meters per second to the right. I know I calculated the force earlier. I'm just going to ignore that fact. Basically start again. So when it says what is the magnitude and direction of the instantaneous force, we figure that out. 1.602 times 10 to the negative 9, 10 to the negative 13 newtons, and it was pointing upwards. So let's actually figure out the radius of curvature of the proton. So again, with the right-hand rule, we know that because the force is pointing up, the velocity is pointing to the right. And by up, I mean positive towards the top of the page, top of the screen. It's going to create a curvature that is counterclockwise. Right? So that's what's going to happen as soon as the particle walks into this magnetic field. It's going to start to curve upwards. And the radius of curvature can just be found by copy and paste from that last page. Can be found by making the magnetic force equal to your centripetal force. Do some quick manipulations, just basically bring the R to the left and bring the QVB down below to the right. One of the V's will cancel off the square of the other velocities, and you're left with this. Essentially your momentum, if you want to quickly call it that, divided by the charge of the particle multiplied by the magnetic field. And after that, it's just a matter of plugging in all of your numbers, which at this point you've done lots before. You guys are experts at it. The units become a little bit messy. A lot of students in the past often will get tripped up on the units, and they'll just assume the answer should be in meters. In the end, it should be. But if you're doing quizzes or exams, you kind of sometimes get lost into what numbers go where, and you won't realize that you made a mistake putting a number in a certain spot if you don't actually track your units down. So I'll be quick about it. The coulomb will be canceled off by that per coulomb, all in that denominator, and then the rest becomes a bit of a mess, so I'll just do it off to the side there in purple. My numerator is basically momentum, kilogram meters per second. My denominator, once the coulombs are canceled out, is a Newton per meter per second. So because I have a per meter per second, in my denominator, I can basically bring that up to my numerator, and now I've essentially got a kilogram meter square per second square, which is a joule, and a joule is technically a Newton meter. So I'll just call it a Newton meter, and then after that you can kind of say, oh, that's how the newtons cancel out. So likewise, you could have gone back a step, go here, and I could have converted that Newton into a kilogram meter per second square, and then everything would cancel out except for that meter. So that's the other way I could have analyzed that. So we're left with a meter, that's what we want, and then the rest is just math. Numerator divided by the denominator gives you roughly 1.666666. I can't quite remember what it was, but if I just use 3 significant figures, which I should only use 2 technically, and this one I did it properly with correct significant figures, I would just call it 17 centimeters, my own work. But if you call it 0.17 meters, that's fine too. Mean the same thing, of course. So radius of curvature, about 17 centimeters, and that's not unheard of. So where's the stuff used? Typically in mass spectrometers. So a lot of chemists actually use physics to figure out particles, figure out what the mass to charge ratio or the charge to mass ratio. I've heard both of them. One is in the inversion of the other one. And they use these mass spectrometers to pretty much isolate individual masses of certain isotopes and certain particles. Maybe they're trying to figure out what particles are in a substance. And so they have to use basically the equations that we just went through to figure that out. So I'll give you a quick little skinny on that. Essentially, a mass spectrometer consists of firing particles, ionized particles. So they ionize them, however they do that. And they pass it through, they want only certain velocities passing through. So what they do first is they pass it through a velocity selector. And the velocity selector usually has parallel plates, charged parallel plates, whether it's positive on the top, negative on the bottom, doesn't really matter. all that matters is you know the direction of the electric field. So when you fire these particles into between these parallel plates, what'll happen is if there's no magnetic field present, so depending if it's a positive charge or a negative charge, doesn't really matter. You can ignore that positive for now, but if it is a positive charge and it's not going fast enough, it's going to follow this projectile path where it will follow the electric field. Electric field is going down, so maybe it will curve down if it's not going fast enough. If it's going slow, it's going to curve down really quickly and hit the front part of the parallel plate. If it's going faster, it might go as far as there, or maybe it might just come out near the end. Or if it's a negative particle and it's not going fast enough, it's probably just going to go in the exact opposite direction and curve to the top. And that's where this magnetic field comes in. If you put a magnetic field, in this case, going into the page, and you have an electric field going straight down, right, from the positive to the negative, that's how electric fields are drawn, what's going to happen on the right here, for this positive particle, if it's going fast enough, and the electric field and the magnetic field, backwards, electric field and magnetic field are balanced in such a way, the particle can actually travel straight through. And so only the particles going at the correct speed will actually make it through the velocity selector, because you're trying to balance out the magnetic force, right? If you use your right-hand rule, particles going to the right, it's positive charge. Magnetic field's going into the page. We just did a question that was similar to this. We know that it should curve upwards. If the magnetic field's too strong, this positive particle will actually follow the path that I said was probably the electron. It would go curl up towards the positive. It doesn't really want to go towards the positive, but the magnetic field is too strong. That's what will happen. If the electric field is too strong, it'll curve downwards as well. So those two things acting together will try to keep a particle going at the correct velocity straight forward. And so you just assume it's a static state. We say that the magnetic force pulling the particle upwards should be equal to the electric force pulling the particle downwards, and you set those two equal to each other and solve for your velocity. Because if you kind of quickly look at it, I didn't show the work, but if you look at it, if you make QVB equal to Q epsilon, the charge cancels out, and you're just left with VB is equal to epsilon, and then it's just a matter of solving for your velocity. So that would be the velocity of the particle that makes it through the first part of your mass spectrometer. Second part, so assuming magnetic field is flipped in this diagram, but it doesn't really matter. Once the particle has been selected for its velocity, it will go through, it'll pass the plate, it's going the correct speed. And at this point, once it's past the two parallel plates, there's no more electric field, and then the particles are free to curve in your magnetic field. So in this case, the magnetic field is drawn, so it's coming out of the page. And so in that case, you're going to curve, a positive particle is going to curve clockwise using the right-hand rule. And so what chemists will do is they'll have some kind of a photographic plate that will start to develop, right? You'll see light spots on it when charged particles hit it. And what you remember about momentum is larger masses are harder to move. So if you have different masses, different ionized masses traveling through this velocity selector, larger masses are going to have a larger radius. So they're going to take more effort just to curve into a new spot on the plate. Smaller masses are going to curve a lot easier, so they're going to have smaller radiuses. Think of a big semi-truck, big rig tractor trailer pulling, I don't know, 2 trailers full of whatever semis pull. They would need quite a few lanes to actually do a U-turn. Whereas if you're driving one of those smart little cars, they look no bigger than a motorcycle, they can pretty much turn within 2 car lanes because they're small enough, right? So small vehicles can turn a lot quicker. They have a lot smaller mass. Larger masses, larger trucks would require a much larger radius. So that's one way they can separate masses and figure out, oh, well, this was charged, I don't know, carbon. Oh, this was nitrogen. Kind of hokey of an example, but that is an example of how they can separate masses of charged particles. So with that then, we can find the mass to the charge to mass ratio, or again, I've seen it also mass to charge ratio. It'd just be the inversion of that. So if you can remember going from your magnetic field, remembering that you have any of those particles are traveling in circular motion, you can create that equation, right? QVB is equal to mv squared divided by the radius, and you can manipulate those two equations to look like this. You can find a charge to mass ratio. And if you remember from 2 or 3 slides ago, the velocity selector, as it's passing through 2 charged plates, parallel plates, if your velocity is equal to your electric field divided by your magnetic field, then you can create a quick little equation, which I think this is actually in your equation sheet from the start of the year. You can find the charge to mass ratio to be the electric field divided by the magnetic field squared multiplied by the radius of curvature. So they use this to determine your basic elements. Like for instance, if you consider oxygen, you know oxygen should just be a -2 charge, and you know what the mass of oxygen is. It's 16 atomic units. You can figure out what that is in kilograms if you are interested, and that should be a set ratio, right? That should be known. Same thing with nitrogen, should be a -3 charge, and mass of nitrogen is 14 atomic mass units, unless I misremember, because I don't have a periodic table right in front of me, and I haven't looked at that for quite a few months. But those things are known, right? They're set in stone. So basically, it's a quick way of determining what you actually have for particles going through those mass spectrometers. So, and you can figure out the units; they're all right there. Another example of where you might see a version of not so much mass spectrometry, but where you could see that as well, is those old television tubes. They're called cathode ray tubes, otherwise known as CRT screens. So what you would have is you would have a magnetic field created by coiled wires, which I'll get into in another video, in the presence of a charged plate. So here's the plates up and down, and you're controlling essentially the current that's going through all of these charged plates and these coils to manipulate electrons going through. And what the electrons will do is they'll either curve up or curve down depending on what signals, current signals are sent through these loops to induce a magnetic field, and that'll basically determine where the electrons hit on your screen. And that's essentially how old televisions were made. A version of this is still kind of applied, but not really in newer models. But because they were so large and they required these large vacuum tubes, people have more or less gone to flat screens, and we don't look back. So I'll stop there because I could ramble for a lot longer. But my stuttering gets the best of me. In your homework, do questions 6 to 18 on page 85 and 86. I'm going to make some amendments because there's a couple things that, again, we cut out from our course. So when you get to question 15, 15A, it says to solve for velocity, but I never walked you through how to work with electrical potential because, again, we lost a month of school, so that one got cut out. Just assume this is what was given to you and ignore 15A, just go straight to 15B with this velocity. And as far as 18 is concerned, just solve for the electric field, not the potential difference. And if you are curious if you did it right or not, just email me and I'll tell you. Okay, have a good one. Email me questions if you have them.